If I write the electron configuration of chlorine in its neutral state, it would be starting at hydrogen, 1s2. That brings me to helium. Then down a row brings me 2s2, brings me to beryllium. Going over to boron gives me 2p, 1, 2, 3, 4, 5, 6. Now I'm at neon. Bump down another, or bump up another energy level brings me to sodium. That's 3s2, brings me over to magnesium. Go over again, brings me to aluminum. I'm in 3p, 1, 2, 3, 4, 5. So this is the electron configuration of chlorine, which tells us where every electron, all 17 of them in chlorine, are to be found. We can double check to make sure we have our 17 electrons. 2 and 2 is 4, and 6 is 10. 12, 17 electrons are accounted for. And it tells us that each electron's distance from the nucleus, these coefficients, these quantum numbers, as well as the probability distribution's shape of where that electron can be found. Remember that those shapes, there we go, correspond to particular shapes. S's are just spheres, really big spheres, and can hold only 2 electrons. So how does it hold those 2 electrons? Well, 2 electrons can't be in the same place doing the same thing. Much as 2 objects can't be in the same place at the same time, neither can electrons. Electrons can only move if they're moving opposite one another, because they'll be repelled by one another. So if an electron is spinning up, the other one must spin down. So each of these probability distributions, each of these sublevels or sublevels can hold 2 electrons. Each sublevel can hold up to 2 electrons. So this S, which can only hold 2 electrons, is the only shape it'll have. And if one's spinning up, the other one's going to spin down. And once that sublevel is full, then we can start filling in some of the P's. And if one spins up, the other one has to spin down. One spins up, the other one has to spin down. This is the principle of an orbital diagram, where you show each orbital and the electrons that correspond to it. So S's can only hold 2 electrons, and therefore will only have space. We'll only make one space for them. P's, you can have up to 3 directions a P can go, left to right, top to bottom, front to back, and therefore we can have 2 electrons on each, so we'll have 3 spaces for a total of 6 electrons in the P orbital. When we have D's get some crazy shapes, but the long and the short of it is that D orbitals can hold 10 electrons, and so we'll have, you guessed it, 5 spaces for any D sublevel. F's can hold up to 14, and therefore we'll have 7 spaces available to them. If you were to graph the energy of an orbit, it would look like this, where the closest orbital is closest to the nucleus. I know that's slightly counterintuitive that the lowest number is on the bottom, but because it's the least amount of energy. I guess that's not counterintuitive. I guess that's just common sense. Imagine that. But the lower the number, the closer the electron is to the nucleus, and therefore the least amount of energy it has. So 1s, any electron in a 1s orbital, is going to have less energy than anything in a 2s orbital, or a 2p, or a 3s, and so on and so forth. But because electrons want to get to this nucleus, they'll go to the lowest energy level they can possibly get to. This is called the off-bow principle. And when I was in high school, I had to memorize this picture here that you couldn't fill up until you made it all the way across and down an orbital. But I don't expect you to do that. When I say draw the orbital diagram, I'm going to show you how to do it without memorizing the off-bow principle. But just so you know, if you're ever on Jeopardy, this diagram corresponds to the off-bow principle, that electrons go to the lowest energy configuration they can find, closest to the nucleus they can get to. So if there's a seat open, if there's a space open in a 1s orbital, they're going to get there one way or another. So let's say I want to fill an orbital diagram for chlorine. Well, I'm going to start by talking about the first electrons available, so 1s. And s's can only have space for 2 electrons. They can only have 1 electron moving up, 1 electron moving down. So we're just going to put one line over any place we see an s. Next up, we talk about 2s. So I'll put 2s on here. And once again, because it's an s, it can only have 2 electrons, so I'll go ahead and put just one line over that. Next up, we have 2p. Now, unlike an s, a p can have up to 6 electrons. So if each line represents 2, how many lines am I going to give p? If you said 6, you're on the ball this evening. After 2p, I see 3s, so I'll go ahead and put that in here as well. And since it's an s, it gets a single line, because s's can only hold 2 electrons, so why give it more lines than it needs? Give it just 1. After that, I see 3p. And as I said before, p's can hold up to 6 electrons, so if I've got 6, each line represents 2, so 6 divided by 2 is 3. So I'm going to put 3 lines above my 3p. Alright, now I have a blank orbital diagram, one that needs to be filled. So how do you go about filling this? Well, you're going to fill it with up arrows and down arrows. An up arrow represents an electron that's spinning up. A down arrow represents one that's spinning down. So 1s2, that means I have 2 electrons, so one will spin up. And then where will the other one go? Well, it's got to be the other one that will spin down. Since both electrons are negative, they cannot spin in the same direction at the same time. This is Pauli's exclusion principle. They can't be going at the same direction at the same time in the same place. They're going to collide and the world will end. That's probably not technically true. But all the same, the rule stands. When one spins up, the other one can't spin up as well. 2s. I have 2 electrons in, so one spins up, and Pauli's exclusion principle states the other one has to spin down. 2p6. Alright, so 2p6. Think of them like seats on a bus. You're not going to sit next to someone on the bus unless you have to. Electrons are the same way. So the first electron goes in, and it's just arbitrarily, I'm going to say, it's going to spin up. The second electron goes in, it's going to spin up as well. It's not going to sit next to that electron. This is Hund's rule. And it states that that orbitals are filled up one slot at a time, and then they start doubling up if they have to. Electrons won't double up unless they absolutely have to. They're negatively charged. They do not want to be near each other. And I use the word want in very loose terms because electrons want for nothing. So the third electron is going to take up this last seat. And now electron number 4 has to start doubling up. Same with electron number 5. And lastly, number 6. Because this is a lower energy level, it's not as though those electrons are going to jump into this 3s orbital that's at a higher state. It's further from the nucleus. Why be up here when they can get closer to the nucleus down here? So 3s has 2 electrons, one up, one down. 3p has 5 electrons. So the first one goes there, second one spaces itself out, third one's going to space itself out, and now for number 4, it has to start doubling up. And same with number 5. So here is the orbital diagram for chlorine, for neutral chlorine. What if chlorine were to form an ion, get a negative charge? What happens? Well, that means poor chlorine, it picked up another electron. So it gains an electron. Where is it going to gain that electron to? It's going to gain it to its outermost orbital, its highest energy level orbital. So this 3p5 becomes 3p6. So that becomes 3p6. And where does that last electron go? Well, it's going to spin down in this final space available. 3p6. Doesn't that looks very nice, doesn't it? Everything nice and filled. This is the reason noble gases are inert or unreactive, because they have no open spaces for electrons to move in and form a bond with. This is the reason why ions form, to become more stable and to become less reactive. Chlorine, with one electron missing from its p orbital, is extremely reactive, but chlorine, chloride, the ion, is less reactive. Now, one of the cool things that comes about from orbital diagrams is the ability to tell if something is magnetic or not. Now, there are three types of magneticity. We're going to pretend that's a word. Something can be paramagnetic, diamagnetic, or ferromagnetic. If something is diamagnetic, it means that it is not magnetic. Is not magnetic at all. It does not have any sort of magnetism to it. Things that are diamagnetic have full subshells. Everything is full. So if chlorine forms its ion, chloride, and all of its subshells are full, it's diamagnetic. If something is paramagnetic, then that means that it will develop a magnetic, it will be magnetic if something else is also magnetic, if it's placed in a magnetic field. And anything with open subshells can be paramagnetic. So chlorine, just the element, which doesn't exist, would be paramagnetic because it has an open subshell. How paramagnetic it is depends upon how many subshells are open. So if, for example, we lose some of those, this would be paramagnetic to the third subshells. So 3 subshells are open, therefore it would be 3 times as paramagnetic. Ferromagnetic means that there's an unequal distribution of the electrons inside of something, and it has these magnetic fields running through it. And when it's placed in the magnetic field, all of the fields align and it becomes magnetic. Most magnets that you deal with in this classroom are ferromagnetic, meaning they've been exposed to a magnetic field, and now all of their magnetic fields are in a line. If you were to drop one, though, it would disrupt that line, and we would go back to having something that was not magnetic. The way that you can remember this is diamagnetic means something magnetic dies. There is no magnetism. Dimagnetism, die. Paramagnetic is kind of parroting what everyone else does. Well, if you're magnetic, I'll be magnetic, but you have to be magnetic first. And ferromagnetic, well, that just sounds strong. I am ferromagnetic, and I am always magnetic, unless you drop me. Ooh, better idea. Pharaoh, like leader of Egypt, he led everyone, and ferromagnetics would lead other magnetics. Don't drop. Okay, you know what? You come up with your own analogies.